CERN for climate change, what I'm really arguing for is dedicated, absolute top of the range supercomputing, which these days is exascale, 10 to the 18 flops per second, floating point operations per second, dedicated to climate change. And that's not happening at the moment anywhere around the world. If I'm talking to a climate skeptic, I would say, look, you surely are as interested as I am, or as a climate, somebody that's very concerned about climate change, to know the truth. How bad is it going to get? Solving the laws of physics is the only way we have to deal with this. We can answer this question. There's no laboratory experiment we can do to emulate climate change.
Any sufficiently advanced technology is indistinguishable from magic.
Welcome, friends, to another wonderful edition of the Into the Impossible podcast with our guest, Tim Palmer, the Royal Society research professor in the Department of Physics at the University of Oxford, who pioneered the development of operational ensemble weather and climate forecasting, and in 2007 was formally recognized as having contributed to the Intergovernmental Panel on Climate Change, and received a recognition for that via the Nobel Prize, the Nobel Peace Prize that he shared along with many other scientists, and also former Vice President Al Gore. And there's a lot of connection here in San Diego at the Scripps Institution of Oceanography, all sorts of good stuff, many, many good connections. But this will be part of our continuing sequence of Think Like a Nobel Prize winner. Although I can't say that Tim is my first non-physics Nobel Prize winner. He didn't win it in physics, not yet, at least, but he did at least participate in the Peace Prize. So you're my first Peace Prize co-recipient. So Tim, thank you so much for joining us on this auspicious occasion of the publication of this wonderful book. Thank you.
It's a pleasure. Thank you.
So we've had on a fair number of Oxonians. We've had on a fair number of physicists that focus on the biggest picture topics one could imagine. And you were actually referred to me by our mutual friend, Sabine Hassenfelder, who is a recent guest on the podcast, with whom you've written some wonderful works with, and with whom you and I co-recorded a video. This is actually our second video together. We did a very, very technical expository video on the differences between British English and American English back on the first of the year or thereabouts. So we'll put a link to that somewhere up here, down there, wherever. So it's our second time together, Tim, but this time it's synchronized so we can actually have a conversation. So great. Tim, as I mentioned, what I love to do is talk about books on this podcast. And I love to discuss the thought process behind the book, and kind of we'll get into your process. You're remarkably productive, and I want to get into your habits. And we have a lot of young scientists that listen to this podcast, and learning from folks like you who do so much in so many different fields, from gravity to the brain to God. We're going to get into it all. And of course, chaos and climate change. I want to ask you, where did the title of the book come to you from? I understand that took some figuring out, and the subtitle, which involves our chaotic world. And most importantly for us visual learners, what is the depiction, the illustration on the cover meant to evoke in the reader's minds?
Okay, well, there's quite a few questions sort of tied up there. Let me start by saying that, you've talked about or at least mentioned my work on climate change, but I've had a fairly, I would say, kind of broad type of career. And I started life off after my undergraduate degree in mathematics and physics, doing a PhD in general relativity theory. So I actually had started off thinking that my life's work would be in fundamental physics, but I kind of reevaluated things after the PhD, and partly because I met some people by chance in the climate area, and I kind of felt that I needed to do something, let's say, a bit more that could have some impact, let's say, on the human species, or some parts of it at least. But working in weather and climate, you realize that weather and climate pretty much affect everything in life, you know, from the economy through to health, through to, you know, whether we have enough food and water to eat and drink. So that in turn got me kind of interested in all these downstream application sciences. And I was kind of, I think it was at the beginning of, probably at the beginning of the pandemic, I was trying to think, is there a theme that kind of unifies everything that I've done? And the notion of uncertainty kind of came up in my head. And that got me starting to think whether I could try to write a popular book, sort of loosely speaking about the science of uncertainty, but kind of discussing it through a range of topics that I've been involved with one way or another. So, and then the actual title, The Primacy of Doubt, was actually taken from a book that James Glick wrote, a very famous biography of Richard Feynman. And Glick is somebody I've known because he, prior to that, wrote an absolutely wonderful book about chaos theory. It really actually, you know, he actually coined the phrase the butterfly effect in the book. This is back in the 1980s, I think.
Yeah.
So I was aware of James Glick and his fantastic ability to explain things clearly. And that got me interested in his biography of Feynman. And then I came across this quote in that biography about Feynman. And Glick says, Feynman, believed in the primacy of doubt, not as a blemish on our ability to know, but as the essence of knowing. And I just thought that was such a wonderful phrase. You know, the notion that the human condition is one of uncertainty, and our creativity comes from being, you know, uncertain about things. And that notion that the primacy of doubt, I thought that really resonated with me. And it's been a kind of I suppose, a philosophy of mine that that uncertainty, you know, is something that you have to put right up front and foremost.
Also depicted on the cover reminded me of Glick's book Chaos, because it seems to have, well, it's a very attractive cover, let me say. So what is the object depicted on the cover, and what is its relevance to quantum physics and climate change?
Right. The front cover is a depiction of what is sometimes called a strange attractor, which sounds kind of a bizarre words to use, but I would say, it's what you would call the geometry of chaos. And it's something that I think, you know, Ed Lorenz, who was the discoverer of this geometry of chaos, should actually himself have won a Nobel Prize. So what Lorenz discovered was three very simple mathematical equations that, you know, you could, I mean, these days they're so easy to solve. They're used as screensavers on computers. In his day, he had to actually get some pretty chunky computing to solve them. But what he found was that when he ran these equations over long periods of time on the computer and plotted the state, so there are three variables. So if you want to describe the state of the system, you need it's a point in a three-dimensional space, which you call state space. And you run your model and you look at, you know, how do these points evolve? And you find that they evolve on this rather strange geometry, which is shown in the front cover of the book. And Lorenz was the one that realized that this geometry actually is a fractal. It's a fractal in the sense that if you zoom into it as much as you like, you'll see the same kind of structures appearing and reappearing. And this is the complete antithesis of the sort of classical Euclidean geometry that we're all taught about at school and stuff, which, like a sphere, the surface of a sphere, which just gets really boring if you zoom into it enough. It just looks flat and uninteresting. So these fractals are distinguished by never running out of structure on the small scale. And actually, as a result of that, you need a different type of mathematics to really describe the geometry of these fractals. And my whole, pretty much my life has evolved around either understanding these fractals or trying to kind of elucidate properties of them. And a lot of the work I've done on predictability of weather and climate has used Lorenz's geometry as a kind of didactic tool. But in the book, I tried to sort of go a bit further and address the question: what if the whole universe evolved on some kind of fractal in some humongously big state space, cosmological state space? The interesting point about that is that because there are gaps in the fractal, there are places, no matter how much you zoom in, there are places where no trajectories ever go. What it means is that worlds that you might conceive of in your head, what we call counterfactual worlds, things that didn't happen that kind of might have happened, may actually be inconsistent with this geometry. And what I tried to show in the book, and I've written papers on this, is that this could be, I'm not saying it is, it could be a new way to understand some of the really puzzling sort of paradoxes and conceptual difficulties in quantum mechanics. Paradoxically enough, perhaps. Yeah. We could talk about that later. I don't want to get bogged down into too much detail.
Yeah, let's kind of start with the astonishing story of a very major character in this book. I don't know what he looks like, but I think his name is Fish, Michael Fish.
Oh yeah,
a man in the Met office where he used to work, and it's concerns an event that occurred about 25 years ago, almost exactly by the time the book comes out. October 16th. 1987, the south of England was battered by one of the most brutal storms to ever hit the country in over 300 years. 15 million trees were blown down, 22 people died, and damages exceeding $3 billion. Worse yet, meteorologists had predicted a nice breezy day. In the aftermath, scientists asked themselves, why was the forecast so wrong?
The weather forecasters admit they got it wrong. They'd warned of a depression approaching, but they had no idea of its strength or direction. This morning, people woke up to devastation and forecasts like this one in the Daily Telegraph. It said the weather would have an unsettled autumnal look.
Really, to have predicted it further ahead in great detail, we'd have needed more information midday yesterday, the midday run of the computer model yesterday, what we call a numerical model, which tries to simulate the atmosphere in terms of equations. That would have needed more information at midday yesterday.
When I heard about the title, the reason for the title coming from Feynman, I actually thought of two other quotes. Well, one from him, which is, science is the belief in the ignorance of experts. That's the first quote I want you to react to. And then the second one is from the famous Lev Landau, who said that cosmologists are often in error, but never in doubt. What is the role of doubt, of doubting yourself, of being uncertain? And how much should people have gained or lost confidence in Michael Fish and his ilk after failing to predict a hurricane and instead predicting a nice breezy day, and then subsequently we'll get into COVID and all sorts of other predictions that are also made by our fellow experts. I mean, that's scientific. So how do you react to Feynman's quote, "Science is the belief in the ignorance of experts"? Do you agree with Feynman?
Well, I mean, the word ignorance, the word ignorance could indicate a complete lack of knowledge. And of course, experts don't have a complete lack of knowledge.
Right.
So I sometimes wonder whether the word ignorance, I've come across that quote myself, of course. I do wonder whether the word ignorance is quite the right word to use. But it's certainly the case, that that someone who, says they're an expert in a field is fallible. So perhaps if we could substitute, the fallibility of experts for the ignorance of experts, I'd feel a bit more comfortable, because certainly experts are fallible.
Yeah.
Now, the Michael Fish storm, I say a few words about it, if you don't mind, because it came at a very opportune time for me, which is in the 1980s. I had, you see, again, we come back to Lorenz's model of chaos.
Good afternoon to you. Earlier on today, apparently a woman rang the BBC and said she heard that there was a hurricane on the way. Well, if you're watching, don't worry, there isn't. But having said that, actually, the weather will become very windy, but most of the strong winds, incidentally, will be down over Spain and across into France as well. Even back in the 1980s, people knew about, and of course, Glick's book popularized the notion of the butterfly effect. So people were aware that because of the flaps of butterflies' wings causing tornadoes in Texas to occur, a week later or something, they were aware that the weather, couldn't be predicted precisely for long periods of time. That was kind of fairly well accepted. But the converse was that if you stick to within a few days, or predicting just a few days into the future, then chaos is not really important, and you can make kind of categorical predictions. It will be sunny, it will be rainy, it will be stormy, or it will be dry, and that pervaded the professional community of meteorologists as well. And I used Lorenz's model to show that the degree of which, if you like, the degree of chaos in an initial condition really varies a lot depending on where you are on that fractal geometry, where you are on that strange attractor. There are some points on the fractal attractor which are actually extremely predictable and stable. Small uncertainties don't really affect the trajectory very much. But there are other initial conditions on other points of the attractor which are incredibly unstable and very, very sensitive to initial conditions. And so I argued that we shouldn't be complacent about weather forecasting, even for a few days into the future, because if we hit one of these exceptionally unstable points, or the atmosphere goes through one of these very unstable points, then we're in danger of making a complete hash of the forecast. And some of my colleagues were kind of skeptical about that, or they didn't think it was something to worry about. But the 1987 storm was just so it was a fantastic example of this phenomenon that, the atmosphere itself is a chaotic system, but the degree of chaos varies and can vary very substantially from one week to the next. And we retrospectively ran an ensemble of forecasts. And by that, I mean we ran the weather forecast model 50 times with very, very slightly different initial states, flaps of butterflies' wings, as it were, introduced into the initial conditions. And for this particular sort of retrospective forecast made 2 days before the storm hit southern England, the spread in the ensemble was just extraordinarily large. I mean, it was just, bigger than you could imagine. And this was just a clear example, as I say, that chaos isn't some kind of fixed quantity that, systems become unpredictable after 30 days or after whatever you want, some fixed period of time. It varies, and this is a feature. I mean, this is the second. If there are two themes which run through the book, one is the notion of uncertainty, and the other is the notion of non-linearity. So pretty much all the systems I deal with are non-linear in some way or another.
Right.
And this notion about the degree of predictability varying from one state to another is a feature of a nonlinear system. That really sort of almost defines a nonlinear system. It could be sometimes predictable, sometimes very unpredictable. So the Michael Fish storm
was kind of nature's way. I mean, I have to say, nature came to my help in persuading my colleagues that this was a serious problem, because I mean, you know, there was nothing else on the news for several days. The Director General of the Met Office was under a lot of pressure to resign, and people were just saying, how, you know, we spend all these millions on the State Meteorological Service and they give us such rubbish, you know, advice, or they can do. So this really changed the way things were done. And these days, ensemble forecasting is used around the world. It's pretty much, you know, accepted by the current generation. And it makes a big difference in how you actually go about making decisions. We can come on to that, but one really big area that's changed is how humanitarian and disaster relief organizations decide ahead of time when to send food and medicine and water and shelter and stuff ahead of some predicted storm, predicted extreme event, rather than in the old days where they would just wait for it to happen, the hurricane to happen or whatever, and then go in afterwards. Now they're going in ahead of time, but they use probabilities to make that decision about when to go in and when not to go.
And how does the, you know, probabilistic or statistical nature of this new method of dealing with, you know, climate or weather related issues, say, how does that differ? You know, how does that employ the main features of, say, chaos theory or you know, dynamical stochastic systems? In other words, I remember actually my freshman year, my professor at Case Western, Robert Brown, he made us read chaos in the physics, you know, course about, you know, inclined planes and mechanics and stuff, but we loved it. And he was a student of Feynman's actually at Caltech. But anyway, he, you know, it was very impressive, and we love learning about, you know, calculating fractal dimensions and showing, you know, the actually generating the butterfly or the Lorenz attractor with different exponents, and of course the Mandelbrot set. But I never got the sense that it was actually applied. In other words, you know, does my local? By the way, I should say that there's the extreme span of jobs exist here in San Diego. So the hardest job in the world is being a sportscaster, because we've never won a championship in any major sport, from the World Series of baseball to soccer to football when we used to have a team. But the easiest job to compensate is meteorologist, because it's basically, you know, they throw up a picture. But I've never heard one of them say, you know, the Lyapunov exponent of this fractal dimension of the perimeter of this approaching, you know, we just had a tropical depression blast through here, and it lasted, you know, 3 days longer than anybody predicted. We got, you know, random rain, and so do people actually use, you know, these, aside from the general features of very extreme sensitivity to initial conditions, aside from, you know, kind of scale invariant, are there any applied ways to translate the esoteric and beautiful mathematics of Mandelbrot and Lorenz to something practical where it would improve something in the daily life, whether it be the price of something, the impact of something, or the cause of something? So yeah, can you address the actual?
Well, you mentioned you started to mention a thing called a Lyapunov exponent. So let me sort of follow up on that.
Yeah.
Because in the early days, you know, we were rather sort of blasé about how you would add these perturbations to the initial conditions to generate an ensemble. And it turns out that if you add small amplitude and small scale perturbations into a weather forecast model, in other words, you add, so that a model, you know, would have a characteristic grid. So all of the equations are kind of discretized onto a grid, which, I mean, these days is, you know, is around 10 kilometers. But, you know, go back 30 years and it's near 100 kilometers. So the uncertainties are largest on the scales close to the grid. So you say, okay, I'll add some sort of noise, as it were, to the initial conditions. What you find is that these perturbations actually don't grow at all.
They're completely the opposite of what you might think from the butterfly effect.
Hmm.
And the reason is, or a key reason anyway, is that models have a lot of artificial kind of damping and what we call artificial viscosity to kind of keep them stable, and so that these kind of small perturbations don't suddenly cause the model to kind of what a numerical analyst would call blow up, do something completely unphysical. So we actually had to go about thinking quite carefully about how to construct perturbations that were consistent with our uncertainty in the observational network, but we're also going to have the effect of growing as the forecast ran. So you mentioned the term Lyapunov exponent, and that's a kind of a measure of how a perturbation grows in a chaotic system, and the largest Lyapunov exponent sort of gives you the largest possible growth. So what we did, in fact, is borrow the ideas or the techniques of chaos theory to compute Lyapunov exponents, and the associated perturbations are called Lyapunov vectors. We had to do this within a kind of I don't want to go in and get into technical details, but finite time kind of framework. But basically, we use these techniques from chaos theory for computing how how perturbations grow, and what are the most unstable directions. Essentially, it's what are the most unstable directions, perturbed along those, rather than just randomly perturbing. So that was a kind of an idea borrowed from chaos theory that went right into the operational code. But you're right. Not everything is, and actually one thing that's important to say, and I kind of go into this a bit in my book, is that there actually is a difference between weather and, let's say, Lorenz's model of chaos, or Mandelbrot's attractor and all this sort of stuff, which is, and again, it relates actually to Lyapunov exponents, which is what we would call the dimension of the attractor. So how many unstable directions are there? How many growing Lyapunov exponents are there? And for something simple like Lorenz's model, there's just a couple. But for the weather, we think there are billions and billions and billions. I mean, it's essentially, we're dealing with, in the real weather world, a very, 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 very large dimensional chaotic system. And actually, in the book, I go into the reason why, despite the fact that the underlying equations, for example, the thing called the Navier-Stokes equations, which are equations for fluid motion, even though they're deterministic, in other words, they don't have any random terms in the equations, because we are dealing with a finite truncation of a system that, for all practical purposes, actually has an infinite number of degrees of freedom, it's actually advantageous to add stochastic noise, you mentioned the word stochastic there, to the equations, the computational equations, to represent properly all of those kind of unstable directions. So again, stochasticity is something that we've taken from the kind of more, say, theoretical ideas in chaos theory and applied them into operations.
When we look at the delightful figures in the book, and we'll flash some of those up right. In the animated version, I had the hardcover and the ebook, and there'll be an audiobook at some point. It's wonderfully and beautifully illustrated, and the illustrations really do convey, the kind of really the relevance of this new way of thinking mathematically that is not that new, actually. I mean, as I said, I remember from a freshman year, 30 years, 25 years ago, whatever. But nevertheless, in terms of its applications and what it can be useful for, and of course, looming throughout the book is also the specter of another, worldwide event that had global implications, and it's of course of COVID-19. Which we're still dealing with in various incarnations. I've just got over a bout of it. And I want to ask you, before we get into, and without getting into political kind of discussions, because there's so much potential for that in both the climate and COVID and economics and all sorts of other issues in the book. The one safe space is when we'll talk about Bell's inequality. I don't think there's any political ramifications of that we will be tiptoeing around minefields. But what are the similarities with something like a pandemic, aside from the fact that we had people, in both, they're both features of the UK, or people in the UK, predicting dire outcomes and then changing it. I guess another Neil Ferguson, not the one who's on this podcast a few weeks ago, but another one in Imperial maybe. Anyway, what could we apply from this additional way of thinking about mathematical, the chaos and attractive states and bistable and so forth, sensitivity to initial conditions? What is the relevance of that to something that we've really known about for hundreds or thousands of years, a global pandemic? Is there a relevancy of this mathematical way of thinking with these kind of features that are similar to chaos theory towards a better comprehension of the spread of a pandemic like COVID-19?
Yes. Maybe I could just quickly comment on the figure that you just quickly showed, because that illustrates also very nicely an example of the type of kind of intermittent chaos.
This one?
Well, it wasn't that. You showed a picture of planets, of a
planetary orbits,
of a three-body orbit, which look, I mean, I recommend anyone to go to the actual online animation because it's just phenomenal. What you see are these four bodies rotating around each other in kind of what look to be they look to be perfect ellipses.
Yeah.
And you watch this for a while and you say, oh, this is boring. I mean, why am I watching this? And the reason you're watching it is all of a sudden, seemingly out of nowhere, the planets just spiral off to infinity. It's like they hit this. It's exactly the same as the Michael Fish storm. They hit this point of instability, having been, potentially for millions of years, just trundling around each other, minding their own business. They hit this point of instability and they suddenly zip off to infinity. And this is just a lovely example of the same notion as the Michael Fish storm. And I try to argue maybe the global meltdown in 2008 the financial meltdown was another example of that. Now, coming to COVID, I think what I was struck by was the analogy in some ways is actually better with climate change than weather forecasting. So I have a chapter talking about how ensembles are also used to make, well, I'm going to say the word prediction, but perhaps that's not the right word to use in this context, because if you think about climate change, the reason we're concerned about climate change is that we're emitting greenhouse gases into the atmosphere. They warm the planet and they change the weather. But the extent to which the extent to which the weather does change is a function of how much we continue to emit carbon dioxide. If we suddenly, for some reason, tomorrow stopped emitting carbon dioxide, then we'd be looking at a very different climate by mid-century than if we just carry on as per normal. Now, we can't, I can't, I don't think anyone can predict what we will decide to do about our emissions. So when you're making predictions of climate change, they're predicated on a particular assumption about whether we'll continue to emit as normal, whether we'll cut back a little bit or we'll cut back a lot, and so on. But we still have to use ensembles. So just running one model with an increase in carbon dioxide is not going to give you a reliable result. You need an ensemble which span the uncertainties in the equations and so on. And again, you essentially have probabilistic estimates of future climate change. Mm-hmm. Now, the COVID thing is kind of similar to that in the sense that, the governments around the world had to make decisions about whether to
impose lockdowns, or let people just carry on and hope for the best. So, and again, those are not, nobody's going to be able to predict that. So what the COVID modelers do are make, and they use the same words actually that climate change people do, which is projections. They're projecting what the COVID deaths and COVID hospitalizations will be, given certain different potential policy assumptions. One policy assumption is that we do nothing to restrict people's interactions, and then another one we restrict them a lot. But again, because the models are imperfect models, they're particularly imperfect, of course, when we're dealing with social interactions and so on, then ensembles, and this was realized actually quite early on, I think, in COVID modeling, that in the case of the Imperial College model, they would put some stochastic representations for uncertain parameters. But in the US, they did something which was actually much closer to what IPCC does for the climate change assessments, which is they made use of the fact that many different institutes in the US had developed their own epidemiological models, and a few people kind of took the lead in ensuring that the predictions and projections were done in a fairly coordinated way with similar types of data output. So everything could then be analyzed in a central hub in a probabilistic way. So I wrote a chapter about COVID because it did strike me there was remarkable kind of similarities in the science. Interestingly, there are remarkable similarities in maybe that's less remarkable, but in the political, I know you don't want to talk about politics, but the people that advocated doing nothing much about climate change were typically the same people that advocated doing nothing much about restricting interactions in COVID. So that was kind of an interesting parallel there. But scientifically, there's a lot of parallels between climate projections and COVID projections.
Yeah, and I wonder.
My only kind of comment at the end was that just as the UN World Meteorological Organization pretty much masterminded the production of these IPCC reports by coordinating climate modeling groups around the world. So I think perhaps the World Health Organization could do something similar for this type of epidemiological modeling. In other words, get groups around the world to do their projections in a coordinated way. They have so you can kind of compare and contrast them and produce probabilistic analyses and so on and so forth. So I hope that'll be something WHO take on.
In the book, you talk a lot about kind of a CERN for climate change, and I couldn't help thinking, well, maybe a CERN for some kind of a global pandemic. But of course, there's a great deal of skepticism about both of these things, some in good faith, maybe some in out without it. But how on a personal level, how do you react to, I'm just looking at headlines from Apple News today. Wall Street Journal reports energy prices soaring across Europe due to their reliance and their cancellation of nuclear energy, for example. Germany gets most of its energy now from coal after years of wind subsidies. Coal is reliable, so it is more beneficial. Hospitalization rates for COVID are very misleading. This is in the Atlantic. They are come in after the fact, and they get retroactively diagnosed, according to the Atlantic. Now, this is not a political show. As you know, I believe that astronomy is a safe space, and cosmology and physics, because no one wakes up and says, I hate that Republican constellation over there, or that damn Tory asteroid. But Tim, how does that affect you when you see, headlines like these that are casting doubt, maybe, or maybe it's where the scientific becomes political? What advice do you have? Do we really need to invest more money to have global consensus and have, CERN costs tens of billions of dollars to construct and tens of billions of dollars to operate? How would we go about convincing somebody, your new prime minister, to invest in something like a CERN for climate change? What would be some of the arguments, or a CERN for COVID?
Well, I don't know about a CERN for COVID because I'm perhaps not, I'm not sure I'm the right person to talk about that, but I can certainly talk about a CERN for climate change. And the issue, the issue comes back to what I talked about earlier, which is we're dealing with a very, mathematically speaking, a very large dimensional chaotic system. So large dimension means it really needs a very large number of variables to simulate it well. A typical weather forecast model these days would have several billion variables, represented. And you can very easily show that if you skimp on that, then your hurricanes don't become as intense as they were before, or your droughts don't become as long-lived as they were before. Extreme weather, becomes less extreme if you start skimping on degrees of freedom. Now, if you're making a 10-day weather forecast, you can pretty much run a model with a billion or more degrees of freedom on a large but not necessarily absolutely top of the range supercomputer. I mean, a petaflop computer would 10 to the 15 floating point operations per second would do pretty well. But when you come to climate, where we're trying to make these projections over 50 years or so, we're trying to say what's the, like California, what's California going to be like in 50 years time? And a key question which for example, a key question to ask will be, how does climate change affect the likelihood of these La Nina events? Because La Nina is certainly a contributory factor for all the drought and the fires and things that you've had. So it becomes a complex question, and I very much am of the view that the sort of computing capabilities that a university group would have, or a typical national institute. You mentioned the San Diego Scripps Oceanographic Institute, world-leading institute, but it doesn't have the compute power to do this type of calculation. And I would, by a CERN for climate change, what I'm really arguing for is dedicated, absolute top of the range supercomputing, which these days is exascale, 10 to the 18 flops per second, floating point operations per second, dedicated to climate change. And that's not happening at the moment anywhere around the world, but a kind of an international consortium. It actually, we're not talking about billions. We're talking about maybe 1 to 200 million a year. So it's not a big deal. It's it's a satellite program or something like that. I don't know. So for me, it's kind of a no-brainer. It comes, if I'm talking to a climate skeptic, I would say, look, you surely are as interested as I am, or as a climate, somebody that's very concerned about climate change, to know the truth. How bad is it going to get? This is the only way we have to solve this problem. Computing or solving the laws of physics is the only way we have to deal with this. We can answer this question. There's no laboratory experiment we can do to emulate climate change.
Is it right? Yeah. Is it even possible, though? I mean, you make a very, very clear distinction in the book between things that are complex systems and things that are merely complicated. I always say, like, building a 787, jetliner is incredibly complicated. It's hard to do. It could take an individual, a billion years to do it. But if he or she follows the instructions, has the raw materials, puts them into parts, and et cetera, it can be done. On the other hand, it seems to me the smallest possible, and you should define for my audience the various definitions of complexity, so forth, but the smallest possible system that's capable of modeling global climate or even weather is the climate itself. In other words, it's kind of an old school analog computer, and unfortunately, you get the results after the event. But there's no letter from God that says you have to be able to predict things in the future, right? So, what do you make of the fact that perhaps it's not just mere computing power? I mean, and I'm saying mere, I don't mean to denigrate it at all, and I think it's absolutely necessary, but maybe that's not enough. And could it be the situation requires a literal global scale computer, not just a global collaboration of computing power?
Well, let me just say, look, I mean, why are we trying to do this in the first place? And I would say perhaps the number one reason is that countries around the world now are having to face the fact that climate change is a reality. And part of the spending is going to be on how to make society more resilient, how to adapt to climate change, the climate change that's already going to happen. Pakistan, great example. I mean, what do they do if these things are going to hit? These floods that we've had in the last couple of weeks are going to hit them every few years now with kind of unbelievable intensity. How is that country going to adapt to climate change? But there's a sort of subtle question, actually even taking Pakistan in mind, because at the moment we're kind of in a very much a sort of transition phase where the weather patterns are staying pretty much as they are, but the temperature's getting warmer. The air holds more water, so when it rains more. But in the next couple of decades, what we're going to start to see are more dynamical effects. So the circulation patterns are going to start to change, and this is really a key question. Then, if you're adapting to climate change, if you're a country in Africa or Southeast Asia, you have to decide: is my greater threat drought and heat wave, or is it storm and flooding and storm surge and that sort of thing? And very different types of expenditure are going to, you're going to spend money on completely different things if you think the main threat is from droughts and heat waves, or if you think it's from storms and floods. So we absolutely need this information. And as you say, we can wait for it to happen. That's the kind of analog, if you like. And the problem is, again, I mentioned this in the book, that, one of the, at the turn of this millennium, the Clay Mathematics Institute announced the most important mathematical problems that faced the mathematical world at the turn of the millennium, kind of mirroring what David Hilbert did in 1900, announcing what were then the key problems. And the millennium one of the millennium problems was actually about the Navier-Stokes equations. And you could interpret this problem as implying that we don't have a kind of uber theory which will tell us, if you get your model grid down to 1 kilometer, say, you will simulate the climate with, an accuracy of 95% or something like that. I mean, I just wish we could do that, because then I could go to the politicians and bang my fist on the table and say, look, I can prove mathematically, if you give me 100 million a year, I will, simulate climate to 95% accuracy. And I can't do that. But all common sense and all experience in weather forecasting on much shorter timescales tells us that as we increase the resolution of these, we reduce the size of these grids, which means we increase the resolution of the models, which means we're solving these equations more accurately, then we simulate things better. We get extremes better. We get all these things better. So all the kind of evidence is pointing to a kind of a modest investment in one or a few international institutes that can put dedicated exascale computing to get us down to kilometer scale grids is going to make a big change to the accuracy of our models, which are pretty inaccurate at the moment, I have to say, on the regional scale.
you know, I don't know whether your listeners will want to know this fact, but if you are this country in Africa or Southeast Asia that I mentioned, and you look up the IPCC figure, the figure in the IPCC report for how rainfall is going to change. Is it going to get wetter in your country or drier in your country? You'd think that was a pretty basic question that everyone would want to know. Is it going to get wetter or is it going to get drier? For pretty much, most of the globe, the models just don't agree. There'll be this little cross-hatched region of the figure, and you consult the legend, and it says cross-hatching means the models don't agree. So this is a pretty unsatisfactory, I would say, state of affairs. And it's coming because we parameterize all these processes, which are important because we don't have the computing to solve the equations exactly. And the parameterizations are exceptionally uncertain. And
it seems to me that governments are willing to spend enormous amounts of money. We just had a bill in America, good fraction of $1 trillion, and the analysis that I've seen from independent organizations, it'll reduce global temperatures by less than 1/10 of a degree Fahrenheit by the end of the century. And whereas for, as you say, literally 1,000th of that amount of money, you could have exascale computers dedicated to this. And yet I still wonder, because COVID does play a role in the book and in your thought process. I remember back in January 2020, I'd been invited to go to China to speak in Tibet, of all places, where they're building a CMB observatory. And they wanted to show it to me. And I thought, this is great. And I got excited. I'd never been to China. And I asked, I was at dinner at a Friday night Shabbat dinner, and one of my friends had here in San Diego. And one of my friends told me he's been to China many times. And he's like, I don't think you should go there. This is mid-January, because there's this COVID-19. And I had heard about it, but I was like, I've heard all these things and SARS and this thing. Yeah, okay. Hopefully by April, it'll be resolved of 2020. I mean, it is January after all, the invitation. It's like, I'd look a little bit closer. Needless to say, it wasn't resolved, and it might not even still be resolved. Some parts of China are locked down in the end of 2022. But given that we in the US, at least, and I assume in other countries as well, we have, multi-trillion dollars worth of three-letter agencies, from the NSA and the FBI and the CIA. We have all these spy agencies, all these, and they didn't even get, the fact that we should order 10-cent masks for everybody, or, that we should start working on stuff. And not all of that was, because of who is the president or who controlled Congress. I think it was a failure of these huge, sclerotic organizations to translate their discoveries, or maybe they didn't know. And that terrifies me more. If you pay somebody $1 trillion, the very damn least they better know is that, well, China just built this hospital in 8 days that can hold 10,000 people. Well, why would they do that? Forget about the micro or, biology of the organism, just the practical on the ground fact. We didn't do any of that. And my friend knew that all of that in January of 2020. He's not like some spy for the government. So, I guess the question I always have is how do we translate? Politicians are very quick, as you know, to clamor for their particular scientific findings if it agrees with their persuasion politically. But how do we actually get them to listen to people like you and your colleagues to say, look, no, we don't need to outlaw gas-powered cars in America, in 2035. What we need is $200 million a year for 10 years to get better forecasting so that we can adapt, as humans are much better at adapting than we are predicting. So how do you bridge that gap? I mean, you have a share of a Nobel Prize, which is sitting in your office there. How do we get them to listen, not just to the science that furthers their political goals, but to listen to the true science, the good science that you and your colleagues are doing?
I mean, it's a tough problem. I mean, as as a scientist, I can't make decisions, and in a way, all I can do as a scientist is lay out the science as clearly as possible, and
and we just have to hope that the politicians get it. I mean, the politicians did get it eventually, at least here in the UK. They did get it with COVID, although, you know, they were very slow on the uptake. I think the science, of course, the science was pretty uncertain in the initial phase because this COVID was an unusual, I mean, the thing that made it difficult was the fact that a lot of people were asymptomatic. They were carrying it and they could spread it, but they didn't really have this, you know, the symptoms themselves. So unlike normal or more kind of familiar types of diseases, you know, where you get ill and there you automatically go to bed and you isolate. This was one where lots of people were getting the COVID virus, but weren't symptomatic of having problems. So science, you know, there was a lot of challenges for the science in the early phase. But I think in this case, the politicians, at least here in the UK, they did get it. We had a lot of committees and things. But yeah, I mean, I'm very active in at the moment trying to, you know, sell this CERN for climate change idea. I have to say one of the frustrations is that some maybe this was like the real CERN back in the 50s, I don't know, but some of my colleagues, I think, you know, they are nervous that if a new institute was funded, the money would come from their institute's budget. So they might, you know, let's say if we're talking about San Diego, you know, if the US decided to go down this route, would the Scripps Institute find that its budget, you know, was being pared off a little bit to help pay for this, and that creates some, I would say, kind of nervousness amongst some of the community, and this is a problem because when I talk to, you know, the really big scientific advisors in the UK, I mean, the question they immediately ask me, does your community speak with one voice? And I would say, well, you know, there are some people who, and they would just stop me mid-sentence and they would say, come back where they speak with one voice.
That's never going to happen.
And that's an issue which we're trying to kind of get over, trying to kind of convince our friends that, because we'll still need the kind of what I would call the conventional models. You know, there's loads of really important climate work. For example, understanding paleoclimate variations. I mean, that you know, right. That involves running models for thousands, tens of thousands of years. There's no way we're going to be able to run a 1 kilometer model over 10,000 years. It's inconceivable. Yeah. So we'll need lower resolution models for doing, you know, some of the basic science and some of the paleoclimate work and things like that. So I don't think these people actually should feel concerned that they're somehow their pet models are being somehow made redundant. It's just we'll need a hierarchy, and for the really important kind of climate policy stuff. Like next week, I'm going on a committee. This is another example. About this climate geoengineering. Should we be spraying aerosols into the stratosphere if we can't agree on? And I would say, how would you ever make that decision if you had models that had, you know, biases and systematic errors that were as large as the signals that you're trying to simulate with this thing? It doesn't seem plausible that we'd ever sanction such a plan B without having a very good idea. For example, whether the monsoons were going to shut off or the moisture supply into the rainforest was going to shut off. And we're not going to do that unless we have models that can really get these regional details, you know, done correctly and accurately. So I think there's plenty of, I mean, I hope there's enough, you know, this is such an important problem. There's enough space here for a hierarchy of models, from the very simple Lorenz chaos model through to these kind of 100-kilometer scale climate models, which you would use for paleo work, through to the 1 kilometer models, which are going to inform policy for the next 50 years or so. There must be room for all of us, surely.
So I want to transition for the second half of the conversation into into more speculative ideas, perhaps, but maybe not. And I couldn't escape, thinking about the connection between quantum mechanics and interpretation and foundations of quantum mechanics, which are quite popular and have been receiving a lot of attention lately. Many books written about it, but also I think yours is the first book to really attempt to make a connection between, as I have in my notes here, between the butterfly and the bell. Bell being Bell's inequality.
Right.
So
right.
I wonder, first of all, if you can, if you don't mind, kind of recapitulating what is Bell's theorem, what is real, if you don't mind, in a few minutes. What is the nature of Bell's inequality? A lot of people hear it. We've done interviews. Adam Becker wrote a book called "What Is Real" about it. But a lot of people, kind of, what's the big deal? If I go into my sock drawer and I've got a pair of red socks and a pair of white socks, and I go on a holiday, open up my suitcase, and I've got a pair that's a red sock and a white sock, I know for damn sure in my drawer at home there's a white sock and a red sock too. So what is this about we should have Sabina here, to actually quote the exact term that Einstein used, I don't know. I do know that she said that this book, your book, is a whirlwind. It's partly scientific autobiography and partly a manifesto of a visionary. Tim Palmer masterfully weaves through climate change, quantum mechanics into one coherent whole. He is a revolutionary thinker way ahead of his time. So let's weave together the butterfly and the bell jar. What is the Bell inequality? What does it tell us? What is it important? Is it just kind of a mathematical oddity?
Well, let's start with the butterfly, because the butterfly effect is a pretty it kind of conforms, I think, to what most of us think of as uncertainty. The idea being that we can't clearly we can't observe all of the butterflies in the world that flap their wings.
Correct.
The butterflies themselves can see their wings flapping. They're not at all uncertain about the fact they're flapping their wings, but we humans can't see all of that. So really what the butterfly effect is saying is that the uncertainty in a weather forecast comes because we don't have perfect information about the starting conditions for the weather forecasts. So a philosopher would call that epistemic or epistemological uncertainty. It's a kind of a lack of knowledge about the system that you're interested in.
Yes.
And that kind of characterizes, I would say, most things in life, that we don't know things because we can't know everything about the system that we're interested in. And of course, Einstein, that's kind of how Einstein felt quantum uncertainty should be too. It's reflecting something that we don't know about the electrons or the photons, that's kind of going on at a smaller level than we can possibly see. But Bell's theorem, Bell's inequality, or the bell jar, whatever you want to call it, is probably the single most important well, it's a theoretical result, but has been tested experimentally, which I think probably most physicists would say kind of really, I was going to say cast doubt, but that's too weak a phrase. Most physicists would say it disproves Einstein's view.
Right.
So basically, as you say, it's kind of based on an idea or a word which Schrödinger came up with when he was at Oxford, which is this notion that quantum systems can be entangled, and as you say, that gives rise to correlations. You could say it's a bit like two particles go off and one's got a red sock and one's got a white sock or something. So if you observe the red sock, the other one is certainly the white sock. Except that it's not like that, because Bell was an Irish physicist who worked at CERN, and he realized that if that was what was behind this entanglement, that, you know, one electron had a red sock on, and if you measured the red sock, you could determine that the other electron going in the other direction had a white sock. If that was all there was to it, then Bell realized that you could look at these correlations. I mean, basically it's about measuring the spin of particles or the polarization of photons, and you measure them in different ways, and the correlations, you know, the result is a mathematical one where you sum up these correlations, and if uncertainty really was the fact that you know, we didn't know whether the electron was wearing its red sock or its white sock, if that's what it was, then this kind of sum of correlations that Bell came up with would be would have a largest value, a value of 2. So you sum correlations done with different measuring, different polarizers, and you come up with this thing which says if everything is deterministic and the uncertainty is just due to the fact that we don't know everything about the electron or the photon, then this correlation function, summing over correlations from different experiments, is kind of bounded by the number 2. And you do the experiment and you find for certain settings of these polarizers, this number exceeds 2. So there's something gone wrong with your assumptions. And most physicists would say that the assumption that goes wrong is that uncertainty is epistemological, and that really what's happening is that the equations of quantum mechanics are intrinsically uncertain. It's not like, it's like the butterflies or the electrons. If the electrons are the equivalent to the butterflies, the electrons don't know what they're doing. The electrons are uncertain. And since quantum mechanics is a theory of everything, you know, it's describing the world, it's believed at least to be a theory describing everything in the world, then everything in the world, in some sense, including reality, is uncertain. And that is the sort of, I would say, the sort of standard view. Now, there's another way around it, but it's kind of, I mean, it's kind of just as bad, which is to say that when you measure the electron and you see it's got a white sock, that somehow makes the electron on the other side of the experiment have a red sock. So prior to you actually doing that measurement, the electron sort of had neither a white sock nor a red sock. But doing a measurement on one particle somehow instantaneously makes the other particle have something definite. Now, that, again, you know, Einstein didn't like that, quite rightly. He called it spooky action at a distance, the idea that doing something here can instantaneously change something over there. So we're kind of left with, I think, a very unsatisfactory state of affairs. But the consensus view, I would say, amongst the majority of physicists who think about this problem, is that uncertainty in quantum mechanics is, so the buzzword would be ontological rather than epistemological. Ontological meaning it's kind of the notion of reality is uncertain. Well, okay, I kind of came into this many years ago kind of feeling, God, this can't be right, surely, and looking very, very carefully at Bell's theorem again, and from the sort of perspective of my kind of chaos background. And this is what I like to think I'm bringing something which maybe the standard quantum community haven't quite sort of seen in this way, which we spoke a little bit about earlier, which is this notion that when you go through Bell's theorem carefully, you imagine a particle and you imagine an experimenter doing an experiment on a particle. But to prove the Bell inequality, you have to assume that had the experimenter done a different measurement to the one he or she actually did, then they would have got some definite result. And this is sometimes called counterfactual definiteness. And, you know, in life, we tend to, I mean, we all use kind of counterfactual reasoning to some extent. Oh, God, if only I had done this and not done that, life would be so much better now. We kind of assume that it makes sense to talk about these counterfactual worlds. But I try to argue from the point of view of chaos theory, it's not a given that a counterfactual world is consistent with the laws of physics. And we talked earlier about these fractal attractors with their gaps in them. And if your counterfactual world ended up in one of these gaps, that would tell you, and the states of your system had to lie on the fractal, then that's telling you that counterfactual that you've just thought up is actually inconsistent with this geometry. Mm. So the short answer is, I personally think, and I have to say, I'm saying this without, probably if you polled an average physicist, they might say, well, maybe it's interesting, but I believe it at the moment. So this is a controversial point of view. But I think there is a way around the Bell theorem which doesn't require you to give up on this notion of a definite reality or have to invoke this spooky action at a distance. Mm-hmm. And that's actually why I wrote a paper with Sabine Hossenfelder, because it comes under the what some people call the superdeterminism, which is not a word I'm terribly keen on. But if it is the case that counterfactual reasoning can sometimes fail you in quantum mechanics, and as I say, I think it can do for perfectly rational and sensible reasons, then your model belongs to this class of superdeterministic models, and I think that is a much more plausible way to understand quantum uncertainty. And it really, what it does then is it brings you back to what I think both Einstein and Schrödinger would have been much more happy with, and others as well. Dirac was pretty unhappy with quantum mechanics, which is to say that quantum uncertainty is actually epistemic and it's not ontological. The laws of physics at their deepest, I think, are certain and definite, and that uncertainty ultimately is our uncertainty.
And what about the person practicing the epistemology or the ontology? In other words, what about the role of consciousness? As you know, your fellow Oxonian who endorsed this book wholeheartedly, saying the very delightful praise that Tim Palmer's book, The Primacy of Doubt, provides a remarkably broad-ranging account of uncertainty in physics in all its various aspects. I strongly recommend this highly thought-provoking book. As you know, Roger's been on the show many times and is a good friend. And he and Stuart Hameroff were on a month or so ago on the occasion of Sir Roger's 91st birthday. We celebrated his 90th birthday last year. And when we discussed it, we got into kind of notions of quantum mechanics in the brain. And we also explored, I asked him to steelman the many worlds interpretation, which, he doesn't believe in. And, what, if any, role that has on or could play in what he calls orchestrated objective reality. Now you have this collapse that is caused, as my limited understanding has it, from some gravitational interactions involving space-time curvature. You've written a lot about his conformal cyclic cosmology. We'll maybe finish up with that in a little bit. But when we talk about the brain and quantum mechanics and determinism, what role does the observer play in your notion of, or what you believe to be this sort of, maybe stochastically and noisy brain that you've also had a recent paper about, and you talk about it in the book. So first of all, noise in quantum systems, in biological systems. What is the role? And is it merely adding, as you said, viscosity, artificial viscosity, so things converge and don't blow up? Or is it really a manifestation of nature, and turbulence and so forth is a feature of the brain? And the noise therein needs to be comprehended as well before we even get to a quantum understanding of consciousness. What is the role of noise in consciousness, if any? Right.
Can I just start with one point you made, because you mentioned the word collapse.
Yeah.
Collapse of the wave function. So in the model which I propose, there is no collapse of the wave function, because the wave function is representing an ensemble
of states on this fractal attractor. So what a quantum theorist would call measurement is actually, it's like ball bearings going into one of two basins of attraction, and some of them will cluster in one basin, and another set of ball bearings will cluster in a different basin. And basically, that is what I see as measurement. It's actually it's where nonlinearity starts to affect the quantum world, and it's clustering trajectories in discrete clusters. Now, I think consciousness doesn't, and I think Roger would agree with this, actually, consciousness doesn't play any role at all in creating, in doing quantum measurement. But where I would sort of take perhaps some departure from Roger is that I don't think there is any collapse at all of the wave function. It's just a kind of transition from a very sort of, I have a particular geometric model where you have trajectories in like a helix, and they're kind of rotating like a piece of rope. They rotate around each other, and then measurement is a kind of splaying of the ends of the rope, and bits of the rope go into one cluster of states, and other bits of rope go into another cluster of state, and these would be called the measurement outcomes. Now, so that's just on that, but on consciousness and noise. So there is actually an interesting kind of story, which is that I've been trying to promote the idea. I think I mentioned earlier in our talk that there is a good reason to add noise to a climate model to represent the degrees of freedom you can't simulate explicitly. And you can show that adding noise actually does help improve some aspects of the climatology of the model. And in the book, I have a whole chapter where again, this is another area where nonlinearity plays an important role. In a nonlinear system, noise can be your friend. It's not your enemy. Typically we think of noise as a nuisance that we try to kind of minimize. But in a nonlinear system, noise can actually help amplify a signal. And I've given several examples in the book of how that can happen. Now, I've been arguing for some years now that noise in climate models is a good thing. And I think probably most people would agree with that now. But still, to this day, we generate the noise by, something I think that von Neumann originally started with, which is what's called a pseudo-random number generator. In other words, it's a piece of code which is perfectly deterministic, but it kind of emulates randomness. And of course, it takes a certain amount of computational energy to run a pseudo-random number generator. So why not make use of noise in hardware? So, we've got all this noise of the electrons going through the chips and so on. And a colleague of mine, Krishna Palem, has pioneered this notion of producing kind of noisy chips where you turn the voltage down across the transistors, so they no longer act as completely bit reproducible deterministic systems. The point is with that is you can then produce noise with negative energy costs because you've turned the voltage down. You're using less energy than you did before. So when I proposed this, I had a kind of commentary in Nature proposing that our supercomputers should have cabinets. Some of the cabinets, not all of them, of course, but some of them should be deliberately stochastic, where we would run, we turn the voltage down across the transistors. We'd be using less energy, so they'd be kind of noisy computationally. And people thought this was a bit of a weird idea. So I had to try and think of an example where, in reality, the system does do this. And I think the brain is a good example of this. So the brain does phenomenal amounts of data processing on 20 watts of energy. It's typically 6 orders of magnitude less than a supercomputer uses, which is more like 20 megawatts of energy, but for the same amount of data processing. So, so what's going on here with 20 watts? Well, we've developed these incredibly slender neurons with very small diameters, 0.1 microns or whatever. And as a result of that, we've managed to cram 80 odd billion neurons into our brain. So when you calculate how much, if you like, energy or power there is per neuron, I mean, it's just a microscopic amount. And the question is it possible that the transmission of electrical energy along axons is actually susceptible to noise? And all the evidence is for these very slender neurons that axons that are in the human brain, they are susceptible to noise. Okay, so is that a bad thing or a good thing? And in the book, I try to argue it's a good thing, and it's probably what's made us the kind of creative species we are. And it's interesting, you talk about, I mean, Roger Penrose is a great example of a phenomenon which is pretty much universal, I think, amongst, people who've had eureka moments, because their eureka moment doesn't happen when they're, hard at work thinking about the problem they're trying to solve. It happens in a completely kind of at a time when you're multitasking, when the brain, all the neurons in the brain are doing different things. And in Roger's case, he was crossing the road, he was talking to a colleague of his, he was looking out for traffic, and then suddenly this idea, which turned out to be the thing that got him the Nobel Prize about how to define an event horizon in a kind of generic way, came to him. And this is very common, that people who when they have their brilliant ideas, it's when they're relaxing or just, doing nothing in particular. And I think this is where the brain, where noise in the brain is most likely to have its biggest effect, when we're multitasking, we're looking around us, we're hearing things, we're walking down the road, we're perhaps talking to a colleague. Then suddenly out of nowhere, we'll get some idea. Now, of course, we have to then analyze whether that crazy idea is any good or not. And 9 times out of 10, or maybe 99 times out of 100, it's not much good. I mean, Michael Berry, the theoretical physicist at Bristol, has a great expression for this. He talks about these ideas that come out of your subconsciousness as claritons, like a particle. But he says the problem with claritons is that in the cold light of day, the logical analysis, which he calls an anti-clariton, destroys the clariton in a kind of particle-antiparticle annihilation. But it kind of makes the point that, actually there are 2 parts to this. One is just the randomness of having these ideas. And then the other is the fact that we have a kind of a more deterministic side to our analytical processing, which kind of then decides whether the idea is any good or not. And it's the synergy between the randomness and the determinism that probably is what makes us the creative species we are. So anyway, the point is, I think that noise plays a really important role in human creativity, and we'd not be the species we are if our neurons were more deterministic. So that kind of provides a good example of why having noisy hardware, might be a good thing. And I would definitely think that, for improving AI, or the prospects of AI being really intelligent, we probably need to go down that route.
Yeah, well, you brought it up, so I can't help but kind of use one of my favorite examples, which you probably know, doing your PhD with Dennis Sciama, who's a titan of 20th century physics and cosmology. But do you remember what Einstein called his happiest thought, Tim? Here's Einstein here.
I do, but it slips my mind.
So he said, I'll give you a hint, Tim. Here you go. Here's a hint.
Oh, I'm falling in the elevator. Yes, that's right. That's right. That's right. I mean, I'd love to know where he thought that. Do you know? Where did he have that thought?
I don't, but bringing on your work,
I bet it was in the bath, or
or maybe playing the violin or something. But
exactly.
Irrelevant to your statement that AI and we'll have to incorporate some of these features. You often hear that AI is going to be capable of reproducing the works of the greatest minds in science and even going beyond them. But that statement has always kind of been a counterfactual piece of evidence against those claims that Einstein said, my happiest thought, how could a computer have a notion of what makes it happy? Or two, how could such a computing device have a notion of what free fall is? I have a computing device here, in my, I can make it do certain things like, computer, turn off the lights, turn off the plug, computer, turn off the plug. There we go. So it'll do stuff for me. It won't unplug itself, though, Tim. I try to get it to do that, and it wouldn't do that. And it won't open the pod bay doors either. I've tried.
Right, that. I know. It sounds a bit.
I tried that with Sean Carroll. It didn't work. So how optimistic should we be? You talk about quantum computing in the book. Is that potential, boon for either topics of foundations in quantum mechanics or in predicting the weather or something like that? Will we have?
Well, I mean, we're getting into a big era here. If we want to talk about quantum computing, okay, I've just written a paper which I'm submitting to the Bulletin of the American Meteorological Society about whether quantum computers will ever be used for weather and climate prediction.
Wow.
And I've called it the good, the bad, and the noisy, because, there are good points. And the good point is that, I mentioned about billions of degrees of freedom. But, you don't have to have that many qubits, which are fully entangled, before you have billions of degrees of freedom. So 30 or something, 2 to the power 30 would give you roughly that sort of thing. So from that point of view, it's kind of looks good. But there's a big negative, which is that at the end of the day, you have to measure these 30 qubits. And it's a bit like it's like saying, instead of with a weather forecast model now, you just say, print out the temperature in the US, and you'll get values for temperature at different places and stuff like that, or rainfall. Right. With a quantum computer, you have to say, is it raining in New York? You have to ask it a question that it will just answer yes or no. And you've only got 30 of these questions to ask. Is it rainy in New York? Is it snowing in Cape Town? Is it sunny in London? Right. And soon the computer will say, I'm sorry, you've run out of questions. That's it. And that's absolutely hopeless, because the amount of data that people need across all the different applications, is more than just 30 questions. So that for me is it is something you don't see discussed very often, that there's the upside to the exponential size of Hilbert space is that you can simulate systems with relatively few qubits with very large degrees of freedom. The downside is you better not want to know very much about your system, because at the end of the day, all you can do is measure those 30 qubits. And that's just too much of a restriction. Yeah. It's like saying if all I ever cared about was how much the global temperature is going to increase, if all I care about is going to be 2 degrees warmer or 4 degrees warmer because of climate change, okay, fine. But as soon as you ask questions about, is it going to rain in London? Is it going to be, hotter or drier in Mozambique or something? Then it's all bets are off. It's completely hopeless. So that's one thing. The other thing I would say about AI is that AI is fantastic for interpolating, but pretty hopeless for extrapolating. And the problem with climate change is it's a problem in extrapolation. You can't just take a look at past data and say, I know what's going to happen in 50 years' time, even if you've got a super clever AI system. And, so again, I think there's a role for AI, there's probably a role for quantum, but it's not a panacea. Absolutely not.
Well, Tim, this has been phenomenally entertaining and elucidating, educational for me, and I know it is for my audience as well. And you've been so gracious with your time. I just want to beg your forbearance for a few more minutes, if you wouldn't mind indulging me and going into the impossible with my fantastic final 4 questions that I like to ask my guests. Is that okay with you, sir?
Right.
Okay. So the first question, they all involve in some way around your late countryman, Sir Arthur C. Clarke. But the first one involves your near-term future, although I hope it won't be for 50 years or more. And that involves what we call an ethical will, and even Alfred Nobel had an ethical will in his otherwise ethical component of his otherwise material will, in that the Nobel Prize was to be given to those who conferred the greatest benefit to mankind. And in that sense, he wasn't just leaving money, but he wanted to agitate towards the improvement of humanity. I want to ask you, in 50, 60 years, when you spring forth the mortal coil that the immortal bard spoke about, what kind of wisdom, not just knowledge, but what kind of wisdom would you want to give over to the succeeding generations to come?
Well, look, I tell you one thing that I feel privileged as a scientist, and I'm sure, Brian, you're probably the same as me, that, you know, we work in our own different fields, but science is very international, and you get to talk to people, you know, from completely different cultures and completely different countries. And the one thing you realize very quickly when you do that is that we all have the same problems. You know, we all have things which we're frustrated about in life. Getting the right kind of, you know, professional recognition, having to earn enough money to keep our families going, and, you know, all the sort of stuff, you know, is kind of universal. And you realize, I mean, I worked for many years at a European meteorological institute, which had, you know, people from every country in Europe. And, you know, we joke about, you know, you can joke about national stereotypes. You know, the Brits are pompous so-and-sos, and they have no taste in food, decent food. And, you know, the Americans, not the Americans, but the Germans. Yeah, no, I won't say anything about the Americans. The Germans have no sense of humor, that sort of thing. So we can make jokes about that. But what you actually realize is that the differences between individuals is much, you know, even within a single culture, is much, much bigger than any kind of national stereotypical difference.
Oh, yeah.
And I think, you know, if I had to, it's not exactly a word of wisdom, but it just bothers me these days. And I guess I'm kind of slightly, I've got bothered by, in my own country, with Brexit, the fact that we seem to be moving away from our European partners and things more and more, that we're all basically the same. We're all got the same issues, the same problems. And if, you know, that you can find a Brit that's got a good sense of humor, and you can find a Brit that's got no sense of humor. And that difference is infinitely larger than any kind of national stereotype between the Brits and the Germans, or whatever it is. So it's really recognizing, if I had a piece of wisdom that science has given me, because science is so international, is that, you know, we're all basically the same. And we've, you know, the more we can, and we're the same on this, in this infinitesimally small planet that's going around the vast universe. The more we can kind of come to terms with that, I think the better we'll get on as a human species.
That's beautiful. So you may know that Arthur C. Clarke is famous for many pithy aphorisms. We'll get into some of them, but one of them was, any sufficiently advanced technology is indistinguishable from magic. We actually open the audio version of each podcast with his actual voice. And just a reminder, you guys can follow the podcast on video and on audio, Dr. Brian Keating on YouTube, and also on audio, wherever you get your podcast. And this will be available on publication day for this wonderful new book. But I want to ask you, kind of in deference to Arthur's 2001: A Space Odyssey, the Sentinels, these weird kind of obelisks or monoliths that appear throughout the movie. We don't really know what they are. Maybe a time capsule, and could be a warning about the future. But if you had access to a time capsule and you knew it would last 1 billion years, what would you put on it or in it? You know, now we're going deep into the future, well beyond your 120th year on the planet.
Well, I think I would. So I'm going to say something mathematical, and I would. I'll explain what it means. You'll know what it means.
I would write the equation. It's not really an equation, but I'd write the sort of mathematical equation, which would say SO2 equals, sorry, SU2 equals SO3.
Yep.
And underneath it, I would say, we know it's true, but we don't understand why it's true. And, you know, I think one of the quotes, I can't quote it exactly, from one of the greatest mathematicians of the 20th century, Michael Atiyah, who worked a lot with Roger Penrose.
Yeah.
He kind of made this point that SU2 is a mathematical term for a group based on complex numbers. So these are numbers, you know, based on the square root of -1. And SO3 is a group which is about how you can rotate objects in physical space and they maintain their symmetry, like a sphere. You can rotate and it still is a sphere. Now, these two are related, but, you know, Atiyah himself, so don't, you know, I'm just getting this from him. He was one of the greatest mathematicians. He said that the complex numbers are somehow the square root of geometry, but we just don't know really what it means. And all my gut instinct is that if we had to understand something that would take us further, deeper into fundamental physics, it's really understanding what this relationship really, really, really means. And so I kind of put that in my time capsule, because I hope in a million years they would say, aha, he was right. He was right to understand. He was right to question that, because we've only understood it 10 years ago, and it's really opened the door to quantum gravity and the mystery of the universe and everything.
Yeah.
So I'd love to talk a bit more about that. But if I write another popular book, I'm thinking I might actually, that might be a kind of a theme of it, because I feel it's really, really something that's important, but we just don't quite understand what it's saying.
Yeah, that is fascinating.
Will that be in my time capsule?
I've always been fascinated by this operation that you can do in classical mechanics, which is to form a Poisson bracket. And you do the exact same thing in a quantum mechanical setting. You make a Poisson bracket, and you get 0 in the classical commutation, anti-commutation relations, and you get, you know, you get the square root of -1, and this funny constant, you know, Planck's constant emerges, and all I don't know, it must be something very deep, right? Because it's saying that not only do you get non-vanishing, you don't get 0 anymore, a rather important round number, as Julian Barbour used to say on the podcast, but you get this square root of -1. Why is that? Where does that come from? And then presumably, I don't know, I mean, you're the right person to ask, but I mean, could you keep going? Are there higher order ways of taking the analog of commutation relations that would give you quaternions and octonions and Clifford algebras? And I mean, is there a whole other set of reality? I mean, we just think quantum mechanics is hard, but really it's just the analog of, you know, the square root of -1. And we know there's a lot more richness, like you just said, SU2. I don't know. Maybe I'm just hopelessly out of my depth here, but I find that.
And I think it's a great question. I'm sort of worried that if we're getting towards the end of the podcast and I start launching into something,
okay,
fair enough. We'll end up speaking.
Let's do that at part 2. So you'll write.
So I'm just going to say it's a really. I think you've absolutely hit the nail on the head. It's a terrific question, and you know, that's what we got to focus on.
All right, great. Last 2 questions really quickly. So Arthur said things like, for every expert, there's an equal and opposite expert. But he also said, when a distinguished but elderly scientist states that something is possible, they are almost certainly right. When they say something is impossible, they are very probably wrong. What, if anything, I'm not calling you elderly, but what, if anything, have you changed your mind on recently, or most pronouncedly in your life? In science?
Well, okay, I'll give you an example, and I say this, you know, you've probably had the same experience as me, or maybe not. Maybe all your papers have been published, you know, with only minor comments from the referees, but
very rarely.
But occasionally we have papers where the referee says this paper shouldn't be published, you know, should reject. And our initial reaction is to say, "Oh, this guy is an idiot." You know, how did they choose him? Or I say him, you know, him or her.
I would say her. Yeah, you gotta be.
Could be a her. Yeah. But I have to say, there's one occasion where I'm just so happy
that the referee rejected the paper. And this was, when the ozone hole was discovered by balloon measurements over Antarctica, it kind of took everyone by surprise, because people had predicted that ozone was being destroyed by the chlorofluorocarbons from aerosols and so on. But then, since we spray most of this stuff in the northern hemisphere, surely it would be the ozone over the Arctic that would be destroyed. Right. So I kind of thought, well, okay, this probably suggests to me that this isn't actually a human effect, but it's something in the dynamics of the southern hemisphere climate that's causing this ozone hole. So I wrote a paper with a colleague and sent it to Nature, making a kind of hypothesis that it was caused by some ocean. It started off in the ocean, the southern oceans, and then the effect propagated up in the stratosphere, and the circulation changes affected the ozone and stuff. And it wasn't rigorous, but we sent it to Nature and it was rejected. And of course, at the time I was incensed, but Nature, it wouldn't. I mean, once your paper's rejected by Nature, that's it, forget it. But my God, am I happy that it was, because this was completely wrong. I mean, it turned out that it was actually caused by human aerosol, emissions, right. And it was a kind of complicated chemical reaction that only happened in the southern hemisphere, because the stratosphere is so much colder in the southern hemisphere than the northern hemisphere. So the temperatures weren't cold enough for this chemical reaction to happen in the northern hemisphere. So that was something where I was completely wrong, and I was so happy that never made the light of day.
Good. Those are the kind of errors you'd like to be wrong about, like Einstein. His biggest blunder turned out to be a great discovery. Okay, last question, Tim, and I thank you so much. I know it's getting late there. Going backwards in time, Arthur C. Clarke's third law states the only way of discovering the limits of the possible is to venture a little way past them into the impossible. And that's the origin of the name of the podcast. I want to ask you, we have a lot of young scientists that listen to this show in their 20s and 30s. What advice would you give to a young Tim Palmer back in that epoch of your life, decades ago, to give you the confidence, the courage, the charisma to go into the impossible as you've done? Advice to your former self.
Well, I guess there are two things. I would say one is read broadly, because I am a great believer in that sort of 90-something% of new ideas in a particular field come because somebody has made the connection with some technique that's used in a different field. So read broadly, don't get too siloed, into one particular thing. And the other thing is, which kind of comes back to what we were talking about the brain and creativity. I mean, if it is the case that you have your eureka moments when you are relaxing, then make sure you give yourself enough time to do that. I mean, don't spend the whole day stuck in front of your laptop or your desktop computer or something, just kind of agonizing about some piece of code or some equation or other. Make sure you have time to do nothing, because that's when, as long as you've got the background, your brain needs the basic material there to make the connections, but the brain does its own thing in making those connections, and just give it the time to do that. And if you're just all spending day and night just focusing your concentration on some scientific problem, you're not going to solve it. So don't lead a balanced life, I would say. don't get sort of seduced into spending 20 hours a day focusing on some arcane problem.
Pick up a guitar, a banjo,
absolutely,
a cricket paddle,
absolutely,
a golf club. You have so many interesting instruments in the back. I can't believe you're not a string theorist. Tim Palmer, such an incredible polymath. It's true. This book, written with such.
I'll show you the Oxford. This is the OUP version. It's got a slightly
Okay.
different front cover. So if
Wow.
you're reading this in the UK or Europe or somewhere,
Very nice.
You have a slightly different cover.
Different cover, same content.
Same content.
Has all the hues and the flavor and neighborhood and all those good things. It makes a worthy compliment to this book. Look, it has a butterfly on the front of it. You appear in this book very prominently, and Sabina kindly appears on the cover, at least in endorsing with her heartiest encomium of this book. Tim, you are a polymath, incredibly impressive. I would like to spend more time at some point, maybe at the occasion of your next book, or when I'm in the UK. I'm supposed to be there next year. Come and visit, and I'd love to talk about hear you play those instruments in the background. That would be such a treat. And so now I want to thank you and wish you a wonderful evening over there across the pond, and hope for the best of success, and congratulations in my heartiest sense on this wonderful book. It was really a joy to read. I devoured it in both formats, and listeners should as well. Thank you, Tim.
Thank you, Brian. That's very kind of you. Thank you.
Any sufficiently advanced technology is indistinguishable from magic.